this because it's equivalent to a thermal effect, so it's quantum but not quantum? That's where my confusion is.
No.
It's stimulate the emission, that's a quantum statement, but why should the analogy really hold? When you, can I invent quantum computing this way? Reinvent it?
Would one want to use this experiment to test quantum mechanics? The answer is no. But we've got loads and loads of tests of quantum mechanics around already. Okay? I think, I believe, if you believe that quantum mechanics is right, then, either of these experiments will tell you that this system actually produces quantum noise with the temperature given by this the derivative of c squared minus v squared at the horizon. As I said, in the Steinhauer experiment, it's much more direct. What he wants to measure is actually also the entanglement between the particles given off outside the horizon and the particles given off inside the horizon. And he claims that he can look at at the measurements that he make and actually see that entanglement between genuine entanglement, not just thermal spectrum, but a genuine quantum entanglement between those two, which is what Hawking would have predicted should one do the experiment in this kind of a system. What he measures, I skipped over that slide, running out of time. Let's see if I can go back. So what he wants to measure is basically NH is the number of particles or the number of these quanta on one side of the horizon. It's basically BH dagger BH expectation value. NP is the number of particles on the other side of the horizon, the partner particles, i.e. the expectation value of B dagger P, B, P, where B dagger and B are the creation and annihilation operators for these modes of the field, minus the expectation value of B times BP times BH. If the two systems are entangled, that should be less than 0. And he argues that in his experiment, that is less than 0. I'm not sure I believe that. But if one accepts that at face value, that's a genuine measure of entanglement. If the two systems, if that is less than 0, then the partner and the Hawking mode and the partner mode are genuinely entangled, which is a quantum system. That's not just correlated, it's actually a quantum entanglement between the two modes. So what he is actually seeing is a quantum emission from the system. He argues also that from that spectrum, from the shape of the curve, from the shape of this curve, he can also measure the temperature. So the system looks sort of thermal. Obviously, there's a huge amount of noise in that.
Since we have to keep all the things in time, maybe just a short question from students and short answer.
Oh, it's too much fun giving a long answer.
Thank you for the talk. We can find the Hawking radiation in another system. Is this mean that there are some extra microstructure we doesn't know?
If you can find Hawking radiation in other systems, does that mean what?
Some extra structure we doesn't know it. Because your field experiment is a classical system, right?
Well, no. I mean, come on. Water is quantum. Bose-Einstein condensates are quantum. I mean, we're physicists. We believe the world is a quantum world. And what we're doing are quantum experiments. Now in our experiments, you could say, okay, well, if I didn't know about quantum mechanics, I just imagined the world was completely classical. I went and did the experiment, I get more or less the same answer. And in that sense, ours is a classical experiment. But as I said, Einstein taught us that that classical result leads to the quantum result if one believes in quantum mechanics. Spontaneous and stimulated emission are absolutely closely tied to each other, is what he showed in 1919 already. And in Steinhauer's, he is claiming to directly measure the quantum properties of this Bose-Einstein condensate, and showing that it behaves in the way that one would expect it to if the Hawking kinds of arguments are correct. Okay? So these systems really are behaving as quantum sources of thermal radiation, similar to what Hawking predicted in his case, similar to what I predicted in the water flow case.
Okay. So, sorry. Short question, short answer.
Was that a short answer?
It's just a yes/no answer. So, yeah. So in all these regards, would you agree that my new proposal of accelerating plasma mirror may provide another more, shall we call, brute force with a much higher spontaneous thermal temperature to investigate this?
I mean, obviously, the higher the temperature is...
Yes or no?
The higher the temperature is, as long as the noise isn't also a lot higher, the better it is. I mean, these experiments, my water experiment was 10 to the minus 12 Kelvin. Steinhauer's experiments are 10 to the minus 12 Kelvin. That's really hard to measure thermal spectrum at 10 to the minus 12 Kelvin. His experiments are a real tour de force, no matter even if his interpretation isn't right. The experiments are still absolutely amazing set of experiments. And one is just so close to really doing the quantum mechanics properly.
But playing your same trick, my flying mirror can be also shined with a stimulated emission.
Sure, no, that's certainly true. And so one could use that system as another way of measuring some of these properties, the moving mirror properties, which are also somewhat related to the horizon of black holes, as Paul Davies way back when showed, various people have shown over the last 40 years. There's a very close relationship to accelerated mirrors and to what goes on in a black hole. So yes, no, I'm not trying to dissuade you in any sense from doing the experiment. It would be great to have that experiment and to get good results out of it.
Let's thank speaker again.